Welcome to Khetz Tutorials, and in this video I'll be doing another contingency table example. But now if you look at this example, there's some incomplete sections, and the first question actually asks for the values. So it asks for us to fill in those empty spaces. So let's read the problem statement first. It says 400 drivers were interviewed about the number of accidents they were involved in during a calendar year. Then it says the results were summarized in the table below. So this is a contingency table. It shows the relationship between number of accidents and the age of drivers, right? So once again, when you add your rows, they should add up to the value over there. When you add up your columns, they should add up to the total, which is down here. So all that you have to do to finish this table, which is part A, you just have to look at the values which are missing, and if you have enough values to find one of them. So if you look here, we basically have two values that are missing, and we can't just predict what to do with any of them. So let's rather go to a row or a column where we basically have enough information to conclude what the value of the missing space might be. So for example, if you look at this row, the total column actually has a value, and along that row we also have a value. So there's only one missing value, so that the total becomes 300 over there. So what we can do, just say 300, because the total of this row is 300 and we already have 200. So we can quickly conclude that the value of C is 100. So 100 should go over there. And now that we have this value, if we look down here, we also have another value. And to find D, all that we have to do is to add these two, so that the total is the total of the column. So once again, you add your rows, find the total there, and your columns, find the total down there. So now that we have a value for C and a value there of 50, you can add these two to get 150. And now we have an additional value here, but not enough information for B, but we actually do have enough information, because the final value that you have here should correspond to the total number of people who are involved, the total number of items if you're dealing with items. So this F over here has to be the total number of people. In this case, we're dealing with people, so expect this to be the total number of people, and it says 400 drivers in the question. So that is what we expect all the way at the last corner, because it will be the sum of that and the sum of that. So that can only give you the total number of people. So that last block over there in the corner, you expect that to be the total always. And since we have this and we have a value at the top, we can find the value over here, which should be 100. So that the total of these two can indeed be 400 down there. And what else do we have? Now that we have a total of 100 and we have 50 along this row, then we can find the value of A, which should be 50 as well, so that the total on the row is 100. So 50 and 50 add up to that value over there. And now if you look at this column, we now have two values, and we can add those up to find the value which is below, which should be 250. And if you check, everything now adds up. We now have all the values that we're supposed to fill in. If you add 200 and 100, you should get that 300 over there. If you add 50 and 50, you should get the 100 over there. If you add 250 and 150, you should get that 400 over there. And if you add the 300 and the 100, you should get your 400 down there. So that is how you check if your values are correct. If everything adds up, then you know that you did the right thing. So that is the first question. We are asked to fill in the missing values, and we did that. And the next question says, is the number of accidents independent of the driver's age? Support your answer with the appropriate calculations. Okay. So now for independence, the condition doesn't change. So let's write the condition for independence. For independence, the intersection of variables should be equal to the product of the probability of each of the variables. So you can choose any part of this to check this, right? So for example, if we were to take the probability of a driver being 40 years and younger, that probability would come from this total over here. This is the total. If you look at the row, that is the total number of people who are 40 years and younger. So you take that total, divide it by the total number of people. Then you take, so this is one variable, the age is one variable. The other variable is the number of accidents. So those are the two variables that we're talking about, or those are the two variables which we're trying to find a relationship between. So now the other variable would be, so now we're dealing with the right-hand side of this equation, the individual probabilities, so that we can multiply them. So now the probability of having, let's just use this column, which is of the probabilities, the probability of having 2 or fewer accidents. And that value you just find down here. The total of people who had 2 or fewer accidents is 250. Divide that by the total. And now we can multiply these two to get the right hand side of this equation. So that would be that multiplied by this. And the value that you do get from multiplying the two is, let me just reconfirm this. The value is 0.46875. So that is the value that you get from multiplying the two. And now let's check the left-hand side of our test. Basically, you don't necessarily have to write the right-hand side and left-hand side. I'm just writing it so that you understand which part of this test equation we are trying to find. So you can't set these things equal to each other because that is what you're testing for. So you'd rather show what you're actually doing. So in this part, the reason I wrote RHS was to show that we're actually talking about this multiplication on this side. So you don't really have to write it, right? So just calculate your stuff and then conclude at a later stage. So you'll see how I'll do that in a bit. So now we're going to focus on the left-hand side, which is the intersection of the two variables. So we're going to look for the point or the probability of having 2 or fewer accidents if you are 40 years and younger. So where's the intersection of 2 or fewer accidents and being 40 years and younger? There's the intersection point. That is where the two variables meet. You can draw a line if you want and see where they actually cross, and that would be a point. But again, you can do this with your eyes, as I previously said in the previous video. And if you haven't watched that video, I just link it on the top right. So the probability of having 2 or fewer accidents if you are 40 years and younger would be 200, which you can take from the table over there. That is the intersection of the two. So that is the probability of that, and that should be a half. Now, if you look at this value is not equal to that value, which means the two variables. So our conclusion comes from this. So the probability of being 40 years and younger and having 2 or fewer accidents is not equal to the probability of being 40 or younger multiplied by the probability of having 2 or less accidents, and therefore the variables are not independent. So what this conclusion says is that we basically might have a relationship between the two, and it does make sense if you look at it from a medical standpoint, that the older you get and you basically make more mistakes, I guess, due to some physical changes, if I can put it like that, or whatever the case may be. But now, mathematically, we now just showed that these two things are not equal, and therefore the variables are not independent. And that is how you basically prove that. So I just wanted to do another example, just so you're confident enough with these types of questions. And that is all with regards to contingency tables. If you like the video, just give it a thumbs up. If you haven't subscribed, please subscribe, and I will see you in the next video.